Hello everybody, in this lecture we're gonna discuss pipelining implementation and hardware. So as we discussed in the previous lecture, we're gonna perform the implementation of this 5-stage MIPS pipeline MIPS processing pipeline. So we know the stages are IF, ID, EX, memory, and write back. However, how can we pause between one stage and the other? So if we take the first element, which is the fetch, this constitutes the instruction fetch. Of course, there's the adder and all the circuitry. PC is controlled with the clock. So at each cycle, an instruction is fetched. Now to pause this, we add something called a pipeline register. So this is the IF stage, and this pipeline register is also controlled with the same clock. So these two are connected together. So what happens is that the instruction is fetched and is waiting here. At this stage, when we go into the ID, this instruction is fed into what I'm gonna call IF over ID pipeline register. So this is between IF and this stage is ID. So this is the instruction. Now with the instruction we can decode this instruction, and from it we can get our controls, and of course we have here the register file. So we have here RS, RT, of course a multiplexer here, RD, okay, and of course we get the immediate. This is sign extended, 32-bit. This is the immediate, okay, and we get the value of RS and the value of RT. Now we have also here register write. Then we add another pipeline register to separate the two stages. And of course it's also connected to a clock. This clock, they are all connected together. So what happens is that at this stage, this is the IF, we fetch the instruction and we wait here. At the next edge, this instruction now goes into the ID stage. We get all the control lines, we know which registers we're gonna use, we know the instruction type, and then we have RS and RT ready, and also the immediate. And then we go to the execute stage. Here we have the ALU. Okay, so of course what we need is RS, which will be here, and RT, which will be here, and the immediate. Okay, of course with the instruction we need to get all the control lines that we're gonna use later on. These control lines will be register write, because we need to know later on if we're gonna write to the register, ALU source in this case, and many others. So of course ALU op to know what is the instruction to be, what's the operation we need to do in the ALU. All of these control lines are fed from here. and many other that we're gonna use later on. So later we have the result. Of course, now we have another pipeline register. Okay. Of course, we have with the register write. I have memory read, memory write, and here we have the data memory. And at the end, we're gonna have the write back into data. Okay, so here we have memory, and here we have write back. So of course the clock is not drawn well, it should be equidistant. Okay, but this is the result, can go here or can go into the pipeline register, and we go all the way back. So the main idea I want to discuss here is that the way we impose a 5-stage pipeline processor is by including 4 pipeline registers. Of course, the 5th stage comes from PC, okay, because it's clocked. So this is 1, 2, 3, 4, 5. So we have 5 sequential elements, and inside this sequential element we corner a combinational circuit. Okay, so this combinational circuit will only change value after the input value is changed by a rising edge on the clock cycle. So let's take an example. Now, assume we have this rough sketch of a 5-stage pipeline. We have, of course, this is IF over ID, this is ID over EX, EX over memory, and memory over write back. So let's start with the first instruction. So let's say I have instruction number 1, this instruction. So first it will be fetched. So if we take the first instruction and schedule it, we have at each clock we have a stage, so that's being executed. So at this edge we have IF, we have ID here, we have EX, we have memory, and then we have write back. As we see, these are the 5 stages. So first, in the IF stage, what I do is I actually fetch the instruction, so that the instruction here will be the add instruction. Then, of course, here we have the control lines. Then I get S0, S1, S2, I get them decoded. So here I need to send, of course, content of S1 to be added and content of S2. Alright, but when I go back, I need also S0 to be sent as an address. Okay, so why? Because when I reach the write back stage, I need also to say, okay, S0 should be, the RD should be S0. Okay, so then I take the value S1 and S2. Of course, here I need to tell that I need to add, I need to take the ALU source should be 0, branch should be 0, and all the control lines that needed for an add instruction. Here we get the result. This is the result that we want, S0, S1 plus S2. And then of course, here I need to say, okay, mem read equals 0, mem write equals 0. Alright, I need to select this result, and at the end I will have RD, which is S0, that's going to go there. We have the result, we have also register write, okay, of this instruction. Fine, and all this information is needed to write the value in the write back stage, which will be at the 5th cycle. Okay, however, when the second instruction is executed, of course I cannot do fetching. I'm gonna do fetch here, ID, EX, memory, and then write back. Okay, so this is the second instruction. So what happens? So if you take the second instruction, this one, so at clock cycle 1 we only have the add. Okay, when 1 becomes here at clock cycle 2, the add is substituted by add I now. So add I will be here. Now when 1 at clock cycle 3, this instruction, the add instruction, will be executing. However, what happens is that add I, instead of S0 and S1, now we have RD still is S0, this will be S0, and then I'm going to use the immediate, which is 1, to do the add I. And so we have now 2 is here, instruction 2 is here, and instruction 1 is here. And at the same time, instruction 3 will be fetched at the third cycle, and we have here an LW. So now 1 is executing, 2 is being decoded, and 3 is being fetched. So if we look at our schedule, of course we're assuming no data dependency. So we go ahead and dial 3, we have IF, ID, EX, memory, now the write back. So this is cycle 1, this is cycle 2, and this is cycle 3. So at cycle 3, what's in the pipeline? We have IF for instruction 3, which is the LW, ID for add I, and we have add is being executed. So at this part in the pipeline, we have 3 instructions. We have, this is the first, the add is here, and then we have add I is here, and LW is here. At the fourth cycle, of course, what happened is that 1 will be here, 2 will be here, 3 now will be the load word, will go into decode, and that now 4 will join the group. So now we have, this is gone, and now this is gone. It's not gone, it's in the second step, and we have now AND instruction. Now add, so AND is being fetched at the fifth. So now we have 1 at memory stage, we have 2 at the execute, 3 at the decode stage, and now we have 4 here. Now as 1 goes into write back, let me use the correct color, 1 becomes here. Now we have 2 now switches here, 3 will be here, and 4 will be here. Okay, and we fetch again SW, which is instruction number 5. So this image shows that the pipeline is full. How come? If we go ahead and continue our schedule, of course assuming no there is no dependency, so we have IF, ID, EX, memory, and write back, and this is the AND, and at 5 we have the SW, which is IF, ID, EX, memory, and write back. So now we notice that at cycle number, this is cycle number 4, this is cycle number 5. At cycle number 5, we have instruction 1 at the write back stage. We have add I at memory, load at execute, and at ID, and store word at instruction fetch. If we look at this image here, we see this is the add. Here we have, and this is what I'm saying. Add is at the write back. Add I is at the memory. Load is at the execute. And it's at the decode, and SW is at fetch. And each time the instruction is going from place to place, it takes all what's needed with it to the other stage. I will elaborate more about the idea of each instruction taking its content from one stage to another. So now if I take a look at this rough schematic of a 5-stage pipeline. So what do I mean by each instruction takes its package with it as it goes through the stages? So again, ID over EX, EX over memory, and then we have memory over write back. So in the fetch stage, the package is the instruction. So if I have add $S0, $S1, $S2, what I will have here is the package will be the instruction in binary, in machine language, will be here. Now this is in fetch. In decode, so in instruction decode, I have the package will be the content of RS, the content of RT, and the unused control lines, and of course RD. Okay, everything that I don't consume in the register file in the decode stage, I go there. With the ALU, of course, it has the immediate and other lines. At the execute stage, okay, now I have the result. I have used RS and RT, I don't need them anymore. I need, of course, RD and the control lines. Same in memory and same in write back. So at each stage, I use some of the information that's passed from one pipeline stage to another and consume the other. Everything not consumed will be transferred to from one pipeline stage to another. Okay, so of course, and this is what I mean, the package is going from one place to another. So this is how the hardware of the pipelining works. Okay, so this is what we mean by having 5 stages. It's all controlled by a clock. Each instruction works in a pipeline. We have a maximum of 5 instructions at the pipeline, and we cannot have more. If you want to have more instructions at the pipeline, then we need to increase the number of pipeline stages. Now, going back into the idea of data hazards, we said that if we have 2 instructions that have a read after write dependency, such as this, we need to stall 2 cycles. And this was evident by saying IF, ID, EX, memory, write back, and we said we will start IF, and then we stall, and we say ID, EX, memory, write back. So they started thinking, is there a better way to eliminate those 2 stalls? These two stalls are severely hindering my pipeline and slowing it down. So what did think about. They said, okay, if I have, this is the add, IF, ID, EX, memory, and write back. And this is the sub. So when in the decode stage we have, let's give some values. So this is 5 and this is 6. Now this is 11. So at the ID stage we have, well, S0 equal 5 and S1 equal 6. At the EX we have the result is equal 11. Here the result is equal 11, and at the write back stage we say, okay, S0 is equal 11, right? So they sort of thumbed. If you look at the sub without stalls, they take a look and said, okay, you know what? The result is already here. Okay, in this stage I read S0 is equal to 5, and let's say S2 was equal to 3. Okay, if I continue like this, the result will be 2 instead of being 8, because 11 minus 3 is 8. The result should be 11 minus 3 is equal to 8. I have the result here to be 11. Okay, they say, can I forward this result from here to here, from this stage to this stage? Remember that this is the time scale. Okay, this is instruction 1, 2, 3, and 4. So here is the past, and now here is the present. So of course this is happening at an earlier stage than the execute. So what if I can do something like this? Instead of using the 5, okay, I will use 11 and say, okay, 11 minus what's S2? We said 3, and the result now will be 8. If I have a way to do this, then I can reduce the 2 stalls to nothing. And this is easily done in hardware. Why? If I take a look back at this schematics. So we have here the add, right? We have here the add, okay? And here we have the sub. So here we have the result, and as we said, it was 11. And if you can take a look, this is 5 plus 6. We said 5 plus 6 is 11, and the result is now we are at the memory stage. So when I'm at the memory stage and the instruction, the sub instruction is going into the execute stage, so I can do something like put some multiplexers here and get the result from here and say, okay, you know what, instead of using, it can be either one, instead of using 5, which it has decoded, okay, use 11. Of course the 11 is coming from here, so easily I can do this result. So as 11 is going, this is the 11 of the add, so now this is 5 of the sub, and the 11 is coming from the add. This is from the add, and now the add is being done in the being propagated through the memory stage, because this has nothing to do with the memory. We're not doing any load, and now I can actually use this value in any of the, if it's RS or RT. This act is called forwarding. So of course we're going to discuss the hardware later, but this, the way of passing a value from a stage that is in the present. Well, this is the stage in the present, and at the present we have add already in the memory, and we already computed the value, so we can actually pass it. And this is what we did by this arrow. This arrow is forwarding values from the execute stage, from a past event, clock cycle number 3, into a future event, which is clock cycle number 4. So I can forward from execute to execute. So let's take another example. This time it's different. Let's take something with a memory operation. So if I have load $S0, $S1, and add $S2, $S1, $S0. So initially, of course, we used to do if id ex memory write back, if stall id ex memory write back. Of course, penalty is 2 stalls. So now let's see if forwarding helps. So let's do the first try. This is first try. So say if id, this is 1, this is 2, so this is load, this is the add. So I have if id ex memory write back. First I need to, if I do it the same on my first try, I'm gonna do something wrong here. So first, initially we used to do forwarding from the execute to the execute. Now S0 is ready at which stage? We all know that load word reads from data memory. So S0 has its value ready at the memory stage. Okay. In 2, how can I, where is S0 needed? So S0 we said in the memory stage is ready, so I need it here. However, the memory and the execute are happening at the same time. I cannot do forwarding. I cannot do something because at the same time I'm reading from the memory, at the same time I'm executing. So I need to stall a little bit. So let's do it. So this doesn't work. So let's do my second try. So with the load, I do if id ex memory and write back. And now with the add, I'm going to do if, I'm going to stall, okay, and then I'm going to do id ex memory write back. So we see now S0's value is ready at the memory stage, right? And I need this value at the ex stage. So I can perfectly now add this arrow. So with this arrow, the value of S0 is forwarded to the execute stage, and this is perfectly fine because this is the past and this is the present. So I can perfectly use a value from a previous stage to the execute stage. So in this way, we just added 1 stall. The previous solution had 2 stalls. So you can say, well, that's not much of an improvement. Well, imagine this was done in a loop of 1000 iterations. So we have just added 1000 cycles in penalty instead of 2000. Okay, so we saved half the penalty using this technique. So just 1 stall and forwarding. This only so when do we need a stall? We need a stall when the value that we need and the value that is consumed are not aligned well. So you see in this stage, memory and execute are concurrent. So we cannot we cannot use the value directly unless we stall it and we have this kind of delay between the execute stage and the memory stage of the first instruction. Now let's consider an example where we want to schedule this program in a MIPS 5-stage pipeline with forwarding. So here we employ forwarding, and we don't have to put two stalls when we have a dependency. So first we start with the first instruction. So of course here we go directly, we have no dependency since it's the first instruction, and then right back. So now we look at the second instruction. We notice here that we have a dependency between the RD and the RT of the next instruction. So we look to see if forwarding will help. So we see here that the value is needed here and is supplied by the execute stage. So now we can add an arrow to indicate that this value is forwarded to the EX stage and no stall is required. Now if you look at the third instruction, let's put this. So the third instruction is a load. It relies on S0. So let's see if we can do a forwarding here. So IF ID EX memory and write back. So we see here that the value is needed because S0 will be written at this stage, so after 5 cycles. However, I have the option of either stalling or actually forwarding from the memory stage since it's directly behind me. So I can forward from the memory stage the value of S0. Since S0 it cannot be forwarded from the EX stage since we only forward the destination. We cannot forward RS or RT. So here we can do a forward from the memory stage because we're not actually forwarding a memory value but the value of the result which traversed to memory to be later written back. So in this way we can have another forwarding. Okay, now if we take a look at the fourth instruction, now here we have S4 which depends on the output of the memory. So here we need a stall and then an ID EX memory and write back, and of course we need a forwarding arrow from memory to execute, otherwise I have to do 2 stalls. At the final we have S1. So here the stall goes down, I cannot write under the stall. I do IF ID EX memory and write back. However, I need the value of S1, so of course I do the forwarding. So here we have concluded the example. So we have 2 rules here. Forwarding can be sourced. This means it can be generated from a previous execute or memory stage. That's the first rule. The second rule is that forwarding to can only be to execute stage. So you see here we're always forwarding to the EX stage. We're not forwarding to any other stage. So the source can be an execute or a memory stage output. We cannot just forward from ID or from write back, or of course not from IF. So always from execute. Now these 2 rules are there for a reason, and we're going to discuss this after seeing the hardware. So if I take part of the hardware where I have the register file here, and I have the stages. I have ID EX, so this is ID, this is EX, this is memory, and this is write back. I didn't include any the IF stage because it's of no importance to us. So we said, okay, we're always forwarding to the ALU or execute stage. So of course the value should come from two places actually. We said, so this is the original value, okay. Another value can come is from actually the instruction after it, so it will be here. So actually we get the value from here, from this point. Okay, so this is execute to execute. And sometimes we also forward from memory, and the value can be either an old EX, so this is an old R format, or it could be an LW. Okay, so this is the line that will take us from actually the old load memory and the old register file. So this will go into here. However, I can depend on either, remember this is the value of RS and this is the value of RT. The second one, of course, will have the same. It can have RT, the normal one. So this is RS, this is RT. And of course, I can have values from EX here. I'm going to extend it to RT, and from the memory. Okay, so if I want to take you back to the previous example to check what's happening, so the first blue line happens when we have this kind of forwarding and this kind of forwarding. However, the red line which is coming from here happens when we have a forwarding from memory to an execute stage, as we see in these two examples. So this is why remember that here we're not forwarding the value of memory, which is fine because we're getting it from this line, which can be a load word or an R format, or can be an I format if it's an add I, for example, instruction that has register write equal 1. That means it's writing to the register file. So this is how forwarding done in hardware. So to choose these multiplexers, we need to have a control line here, should be to have 3, so this should be 2 bits, and this is 2 bits, and I'm gonna call this forward A and forward B, and there should be a forwarding unit that controls FB and of course FA. So this is FA and FB. So how can we detect that there is a forward and what's inside the forwarding unit? Of course, it needs some inputs to work. So let's discuss the forwarding unit and what's inside of it. So to discuss the forwarding unit, I'm gonna write like this here. This is the forwarding unit. And it has FA 2 bits output and FB 2 bits output, which are controlling the 2 multiplexers in the ALU stages. Okay, so we have 2 cases, as we said before. The first case is a execute to execute data hazard, So in this case, let's say we have, let's take the first instruction that we use in our example. So we said add I $S0 $S1 $5, and then we said add $S3 $S1, and then we said $S0. So these two are behind each other. This means we have here add I just finished execution and has the correct value of $S0, and it needs to forward it to this guy here, to the first instruction, which is, or to the second instruction, which is add, which needs S0, the correct value of the S0. So how can we detect this dependency? Remember that we need to find that here we have the value of RS, the value of RT, the value of RD. We have all these values for our forwarding algorithm to work. So we say, so remember, this pipeline EX over memory is the one for add I, and ID over EX is the pipeline for add. So I'm going to write them here in a different color. So pipeline now, where they are in ID, oh sorry, this is EX over memory pipe, and this is in ID over EX pipe. So if I want to draw them here, so this should be EX over memory, and this is ID over EX. So now I want to write the conditions where these should occur. So the first thing, this is the instruction that's causing the dependency. Okay. So to cause the dependency, I need first to say that this is actually reading a value that is dependent on the previous one. So this should be written. So remember, we said that this is a write, a read, after write dependency. So we need a read, which is this one's reading, and this one is writing. So now to know that this is writing, I have a control line that allows you to do this. So I'm going to say if. Now this is the values of this instruction is available here. So register write, a control line that tells me that I have a write to the register file is found here. So I say EX over memory dot register write is equal 1. Okay, this means that this instruction is a write. So I have this done with this instruction. However, there is a special case where I cannot write to register 0 because it's hardwired to 0. So I need to incorporate this, and I'm going to say and EX over memory dot RD not equal 0. Let me write another. This tells me cannot write to 0. Write to $0 or the first register. And I'm gonna write the and. So I have a write, it's not to $0, okay, and I'm gonna say it should be said that if I have forwarding on FA, this means there's a dependency on RS. So I'm gonna say EX dot memory dot over memory dot RS is equal ID over EX dot RS. Okay. This means that RS is equal to RD. This means I'm saying this is equal to this. Then I have, if this is 0, 0, this is 0, 1, so this is the normal RS. This is going to be EX over memory dot RS. Okay, so now this is 0, 1. I'm gonna say, or let's say, forward, let's say 1, 0 is better. FA is equal 1, 0. Alright. However, this is not the case. The case is I have RT, so I need a duplicate condition where I'm gonna say EX over memory dot register write equal 1 and EX over memory dot RD not equal 0 and EX over memory dot RT equal ID over EX dot RS. Now I have forward B equal 1, 0. So again, this is RT, this is EX over memory dot RT. So this is 0, 0, this is 1, 0. Alright, so this covers this case. Now what about the second case where I have forwarding from the memory, which is this line, to actually RT or RS? I need to include this condition, and I'm gonna explain this in a bit. So usually if we have load $S0, $0, S2, and then we have, let's take it the same one as the example. We said that we have $S4 and S0, and then we had and $S1, $S4, $S0. So of course here we have a write and here we have a read. Now if we look at this, the data need to come at a later stage, which is the memory. So this is the memory over write back. So the data should come from this guy here. Okay. Now if I want to add a value here, what should it be? I need to include the case where I have 1, 0. So let me draw this again to make it more clear. So we have the forwarding unit, and this is FA and FB, and we said we have the ALU, and it has 3 multiplexers. It can come from the normal RS, okay, or from EX or EX over memory dot RS, okay, and we have the third one which can come from memory over write back at the second stage, memory over write back dot RS. And the same thing here, we have RT, we have execute over memory dot RT, and we have memory over write back dot RT. So I have 3 sources, one coming from a direct execute to execute, and in this case I have an execute, a memory to execute forwarding, which will be, this is 0, 0, this is 1, 0, this is 1, this is 0, 1, 0, 0, 1, 0, 0, 1. Okay, and then if I take a look at here, what conditions should I add? I should add that from the memory I can detect that there is a dependency. So now I'm going to write the memory hazard. Formulas. Now with the memory hazard formulas, I'm gonna write them on a new page. So we have memory hazard. Of course, I'm gonna start the same. I'm gonna say, okay, the dependency now should be with the memory and the ID, not the EX and the ID. So we say if, this is for RS, if, of course we have double parentheses, if execute, set memory dot write back dot register write equal 1, and memory dot write back dot rd not equal 0, we cannot write to 0, and we need to write the second condition, which is memory dot overwrite back, better keep write back dot rs is equal id over ex dot rs. In this case, for fa will be 0, 1, and for the case of rt we have if memory over write back dot register write equal 1, and memory over write back dot rd not equal 0, and memory over write back dot rs, okay, rt in this case equal id over ex dot rt. Then in this case we have fb equals 0, 1. So in this case I solved these values. So if I take a look at this figure, so remember here we have some inputs. So the inputs will be register write from the memory, RD from the memory, RS from the memory, from this pipeline, and we have also register write from the ID, RD, RS, and of course RT from the execute memory stage. So these are the input for the forwarding unit, and the output is FA and FB, which is controlling these two multiplexers. So given that we have written down the conditions for the forwarding based on a data hazard or a memory hazard as shown in this case. However, there is still a case that we need to attend to, which is called the double hazard, double data hazard. So let's go ahead and explain what is the double data hazard. So in this case, we have the following program. So assume, so it's double data hazard. So now I have add, say $1, which is the first register, $0 for the second register if I am corrected, $2, and then I have an add $1, $3, and add $1, $4. This program may be meaningless because it's overwriting $1. However, it points to a loophole in our conditions. If I write if id ex memory and write back, then I have here if id ex memory and write back. I notice here that we have a dependency, so of course I need to what? I need to forward the value. And now I have a third one, which is if id ex memory and write back. Now I have two conditions which are true. I have a dependency between this instruction and this instruction, and this and this. So what happens, I have now this arrow and this arrow coming from the memory. So I have those two arrows. So somehow here there is no condition that tells me that I need to forward from the EX stage of the previous one. However, the control unit, the forwarding unit, will tell me that FA can be 10 or 01. However, this means from the memory. Sorry, this means from the execute, and this means from the memory. So this means if I label this 1, 2, 3, so FA is 10 from the execute, this is from 2, which is the correct answer, and this is from 1, which is the wrong answer. However, our condition does not note this, so we need to modify those conditions to make them better. So if we look at these conditions, I need to take note of one of them. So now, for this, before this, I need to add a condition that will actually make this not doable. So let's see what I need to add a condition here. I'm gonna add here, and I'm gonna say this is and not, okay, what? EX over memory dot register write equal 1, and EX over memory dot RD not equal 0. Let's put this like this, and EX over memory dot RD is equal ID over EX dot RS. So here I made a mistake. This should be RD and this should be RD. Of course, the destination should be equal to the register, and also here, I apologize, this should be also RD and RD, because we want to know that RD is equal to RT and RD is equal. So these are all RDs. So here, execute over memory dot RD is equal RS, and so this will continue here. So what this condition is telling me? This condition is telling me that if I have a forwarding condition from memory to execute, and I have the same memory condition from execute to execute, I will take, this will be not valid. So, and not, so this will be 0, so automatically I will not do forward 0, 1, and I will do forward 1, 0. This condition is true already. When I said here, this condition is working. So the problem was that this condition is true and this condition is true. So I need to deactivate this condition by adding another condition that detects the double hazard. And it detects it by saying, okay, I have this condition is telling me there is a dependency between this one and this one, and this condition is telling me there is also a dependency between this one and this one. But this not will eliminate the FA equals 0, 1, and it will choose the other one, and I will not have a race condition. Of course, here I have the same thing, but for RT. Of course, one thing I need to mention that here, with the memory hazard, we have to insert a stall. So we didn't talk about how to install, how a stall is inserted. So in this case, let's talk about memory hazards and stall. So a stall is translated into a no operation being inserted in the pipeline. So when I have a load use case where I have a load directly after it, there is a case. In this case, I need to insert a bubble inside the ID stage. So the knob or the bubble, we call it, is inserted in the ID stage. So how is this done? We have LW$S0, $0.S1, and then we have add $S1.S0.S3. So if I take a look at the pipeline architecture, now I have, of course, I have the PC, the program memory. This is IF over ID. I have the decode stage, I have the register file here, and then this is ID over EX. Then I have the ALU with the forwarding unit. Then this is EX over memory. And then I have memory over write back, and this is the data memory. Okay, this is memory over write back. So as we know, we need to actually memory write back IF stall ID EX memory write back, and we have this arrow. This arrow is done by the forwarding unit. But what about the stall? From where does it come? We need to insert a hazard detection unit, and this hazard detection unit needs to be in the IFID and IDEX stage. Why is that? Because the stall is inserted there, and I need to detect early on that we have actually a hazard in this case. So how do we detect a hazard? We detect a hazard when we say that there's a dependency between these two instructions and they need a bubble. This happens when an instruction at EX memory needs values from the stage. So I know for a fact, if EX memory needs value from IDEX, then I need to wait for one instruction before they are ready. And the way to do this is with these conditions. These are the load use hazard. I'm going to say if ID over EX dot memory read equal 1. This means I have an LW or LB or whatever, and ID over EX dot RT or RS in this case, so I won't write it again, equal IF over ID dot, in this case, dot RS or RT, or ID over EX dot RS is equal IF over ID dot RT. Then insert the bubble. So what I'm saying, so why did I use RT instead of this is RT. Why do I use RT instead of RS? So I'm saying if id.rt equal RT of the IF stage and id over EX of RT is equal RS stage. So why do I use this? Because LW is I format and the destination is RT. So if I take a look again at LW $S0, $S1, and then I use add $S1, $S0, $S2. So in this case, I'm saying this is RT, and this should be at the ID EX stage. So at this stage. So what I'm saying, ID EX, if I have a load word here, so here I have a load word, and what's coming is an add or any use instruction, and they have either the RS, in this case, the RS will make this true, or the RT, if it depends on the RT of the previous instruction, then in this case I have a dependency and I need to use the load use hazard and insert a bubble. What happens is that it will insert zeros, and these zeros will traverse the data path as the instruction is executing. So as if I insert a NOP between them so that to separate them a little bit. So inserting a bubble means inserting a no operation between those two instructions. So if this transforms into $S1, then I have a no operation, then I have an add $S1, $S0, $S2, 1, 2, 3. Then I will have the stall ID EX memory write back, and this is the no operation. This is the no operation, and then IF ID EX memory write back. Then I can do this forwarding, and the no operation is the stall that we are talking about. Back to the initial types of hazards. So we said we have 3 different types of hazards. We have data hazards, which we've seen before. We have structural hazard. This comes from read after write. Then we have also structural hazard. This comes from illegal operations. We're not going to discuss this in this lecture. And we have also control hazards. Control hazards happens resulting from a branch. So of course, when you have a control hazard, we have something like a branch if equal $S0, $S1, label, and then say we have an add, subtract, then at label I have, let's say, add I, load W. So what happens is that when I'm doing the scheduling, so 1, 2, 3. So what happens is that when I want to detect that there is a branch, actually the branch is happening at the EX memory stage. Here the branch is taking the decision. So I've already here in the EX memory stage. So I already fetched 2 instructions. So in this case, if the branch is taken, I need to flush the pipeline, which means this automatically convert those 2 instructions to no operations, and I lose 2 cycles. So flushing is the act of turning all instructions in pipeline to no operations. Okay, so I lose 2 instructions. So one method is actually taking the branch instruction and perform it in the ID stage, from the execute to the ID stage. This will save me 1 cycle. Okay, so the way we do it is, we all know that when the branch uses, this is the register file, this is the ALU, so we have these, and then this is 0-bit, and this is the branch conditions. So instead of having it done in the EX stage, I add a small ALU and take the value of RS and RT, and this is the 0-bit. I can take the decision from here, change it to here. So I just add, for extra hardware, which is one, I need the subtractor at the ID stage. I can flush, I need to flush only one instruction, because in this case the branch is taking place here. So I only have I only fetch 1 instruction, and this will save me actually 1 cycle. And this concludes this lecture on forwarding and hazards.